Picture yourself 3.5 kilometers under the Mediterranean. A field of glass spheres waits in total darkness. Then, on February 13, 2023, 21 vertical detector lines registered 28,086 hits. Something had crossed the array. The sensors had not taken a photograph. They had captured thousands of tiny electrical records, each with a place, a time, and a little information about the light that caused it. So how do scattered flashes in the ocean become a direction in the sky? Meet ARCA, the high-energy half of the KM3 Net Neutrino Telescope. Instead of one lens, it uses long strings of light sensors spread through an enormous volume of seawater. Its target is a neutrino, an electrically neutral particle that can travel across the universe without being bent by magnetic fields. Follow that direction backward, and you may find clues about violent cosmic particle accelerators. There is one inconvenient detail. Neutrinos are famous for passing through matter almost untouched. KM3net solves that problem by watching a huge amount of water and waiting for a rare interaction in or near the array. When a neutrino does interact, it can produce charged particles. In the kind of event we're following, one of those particles is a muon. If that muon moves faster than light travels through water, not faster than light in a vacuum, it produces a cone of faint blue Cherenkov light. The neutrino itself remains invisible. You only see the aftermath, photons spreading through the sea toward glass spheres that look in every direction. Now move inside one glass module. 31 photomultiplier tubes face different directions. When a photon hits one, it becomes an electrical pulse. The module records when that pulse arrived and how long it stayed above a threshold, then sends the measurements to computers on shore. But one glowing sphere proves almost nothing. One sensor is struck first. Another sees light a few nanoseconds later. Others follow. To compare those times, we also need to know where every moving module is and which way its sensors point. The ocean is not a rigid building. Currents bend the detector strings, so
Position, orientation, and timing have to be calibrated continuously. Now, the central trick becomes possible.
every hit and color it by arrival time. Without the timestamps, you've got a cloud of scattered dots. Put the times back, add each sensor's calibrated position, and you'll see the cloud develop an order. Reconstruction software tests possible particle tracks against that measured pattern. It asks which path best explains where the early light arrived when it arrived and how the detector should have responded. That is the reversal. The spheres never photographed the neutrino. They measured secondary light, and the system fitted the path most consistent with those measurements. It is not certainty disguised as a picture. It is a direction with an uncertainty attached. Now let's return to KM3230213. Its measured hit times and sensor positions produced a near-horizontal muon track. Researchers estimated that it arrived just 0.6 degrees above the horizon. Watch what happens when we keep the uncertainty visible.
The published 68% containment radius was about 1.5 degrees, dominated by uncertainty in the detector's absolute orientation at the time.
Event's extreme energy and direction made a cosmic neutrino origin far more likely than an atmospheric explanation. Its incoming direction could be extended into a region of sky. That is an extraordinary result. It is also where a less careful version of this story would go too far. Here is the trap you have to avoid. A direction sounds like a destination, but it isn't one. Researchers searched that region using gamma-ray, X-ray, radio, transient, and neutrino observations. They found possible objects, but no association was compelling. KM3net had reconstructed where the particle appeared to come from. It had not identified what produced it, and that distinction is the real power of this machine. It can turn invisible particle evidence into a question precise enough for other observatories to investigate, without pretending the answer is already known. KM3net is still growing. A 2026 status report described ARCA operating in partial configuration with 51 detector lines while its real-time analysis system reconstructed new events. Why care? Neutrinos cross the universe without being steered by magnetic fields, giving astronomy another way to investigate extreme cosmic engines. The immediate payoff is knowledge, not a new gadget, a wider view of nature, and a stronger foundation for future discovery. Civilizations advance when they gain new ways to see. This detector turns the deep ocean into one of them.